Hello there. Today we will look at exponents and the properties of exponents, and we'll look at some problems involving exponents. So before we get into the properties of exponents, let's look at sort of a recap from what we have done before. If we have letter A raised to some power or an exponent n, well, we have learned before that the n here is what we call the exponent, sometimes also referred to as the power. So exponents and power, either one of them is usually referred to. Most commonly, sometimes we say exponent. However, the letter A here has a specific name, and that is what we call the base. So the base and the exponent. Now I'm recapping this because when we start looking at properties of exponent, I'll be referring to the base and the exponents a lot in our discussion here. So, for example, if I have 2 raised to the 4th power, or 4th exponent, the base here is 2, and the exponent is 4. Yeah? Or if I look at another example, if I have 5 raised to the 3rd power or exponent, the base is 5, and the exponent is 3. Now the base, as you will learn later in higher level math courses, the base could be a letter, could be a variable. For example, if I have x raised to the 4th power, the base here is x, and the exponent is 4. So the base doesn't necessarily have to be a numerical number. The base could also be a letter or a variable. With that being said, we will now move into the properties of exponent. Okay, so now that we have seen what is referred to as the base and what is referred to as the exponent, we will now look at the different rules. I will probably go through about 5 of them, maybe 6 depending on what time we have. The rules of exponent, also known as the properties of exponent. What procedure do we follow when dealing with exponents? That's the way we'll go through. How do we simplify it? Now, what I'll do here, I'll write the rule and then we'll look at a few examples. So the first rule I would look at, and the rules that I will write doesn't have any specific order. What I'm calling rule 1 could be rule number 3 or rule number 4 in different books. The first rule I would look at is, how about when we have a to the n times a to the m power. Now if you notice here, the bases are the same. The base here is a, the base here is a. The exponents are different. Generally, this rule states that when multiplying, because we are multiplying here, when multiplying and the bases are the same, we will keep the base. So since the bases are both the same and the base is a, we will keep the base and we will add the exponent. So this is the first rule we will look at. Okay? So once again, when the bases are the same in multiplication, we keep the base and we add the exponent. So we have an example. Example number 1. let's say I have x to the third power times x to the fifth power. Note that the bases are the same. I'm multiplying, so we will keep the base, which is x, and we will add the exponent, 3 plus 5, and that becomes x to the 8th power. So once again, the bases are the same. We kept the base, and we add the exponent. So 3 plus 5, we got x to the 8th. If we look at another example, how about if I have s to the 4th power times letter s to the minus 6th power? Okay? The bases are the same here, so we'll keep the base. And what is 4 plus a negative 6? Well, the plus and minus here becomes minus. So that's the same as s to the 4th minus 6, which is s to the negative 2 power. So here we end up with a negative power, and it's okay, we could have a negative power, but as we will see later on in one of the different roots of exponent, we can simplify this further. So we'll put a star next to this problem, and just telling us that, hey, we could probably simplify this even further once we learn the other rules. Okay? Let's look at another example. Example number 3. How about if we have 5a squared times 6a to the 4th? Well, be very careful here. What is the base? In this example, take a minute and tell me what the base is. Okay? We have seen in our rule that the base is whatever the exponent is next to. So in this case, my base here is a and a. So what we will do is multiply generally. What is 5 times 6? Because those are my coefficient. 5 times 6 we know is 30. Okay? The bases are the same here, a and a. So we keep the base and we add the exponent, 2 plus 4. So we end up with 30a to the 6th power. So we could have a numerical value or a coefficient with a letter. Let's look at another example, one with a coefficient. Example number 4. How about if I have negative 4x to the 6th power times 5x? So as I said earlier, we could multiply the coefficients. So negative 4 times 5 will multiply. That will give us negative 20. And here I have base x, so the bases are the same. So we'll keep the base, but we have 6 plus, keep in mind, there is an invisible exponent there of 1. Okay? So finally we have negative 20x to the 7th power. So be very careful, two things. When you have the coefficient, you multiply the coefficient, and then you add the power if the bases are the same. In example 4, we have bases are the same, but visibly we don't see an exponent there, but there is an exponent there of 1. So it's x to the 1 here. In the last example, example number 5, before we move on, how about if I have negative 2x to the 3rd times 5y to the 4th? Well, the bases here are not the same. So we cannot apply rule number 1. We cannot add the exponent of 3 and 4 because here the base is x, here the base is y. The only thing we could do is multiply -2 times 5, and that becomes -10. And since we cannot add them, we just rewrite the base with its corresponding exponent. We cannot add 3 and 4 because the bases are different. So the general rule applies to any problem with bases are the same, we add the exponent. Okay, we'll move on to rule number 2, or property number 2 for exponents. We've seen in property number 1, when multiplying and the bases are the same, we add the exponent. Rule number 2, I will look at division. What happens if we have a to the n divided by a to the mth power? Well, once we're dividing, because we know the bar here means divide, when dividing, the bases are the same, we will keep the base and we will subtract the numerator exponent minus the denominator exponent. Numerator exponent minus denominator exponent. And I always like to keep these in parentheses for simplicity's sake. Okay? Numerator minus denominator. So there's my rule. And let's look at some examples following rule. Example number 1. How about if I have x to the 7th power divided by x to the 2nd power? Bases are the same, so we'll keep the base, and 7 minus 2, and that becomes x to the 5th power. Okay, bases are the same. We kept the base, and we subtract the exponent. Always numerator minus denominator. The rule does not change. The numerator exponent always first. Example number 2. How about if I have t to the 4th divided by t to the 7th? Well, the bases are the same, so we'll keep the base, which is t, and it's 4 minus 7. And that becomes t to the -3. And once again, we have a negative exponent, which could be simplified later on. We generally don't leave bases with negative exponent. So I'll put a star here, and at the end of the lesson, I would like you to finish the last step here. Let's look at another example. Example number 3. How about if I have 10s to the 7th power divided by 2s to the 6th power? So we see that we have same bases, the letter s, they're the same bases, but once again, we have coefficients, 10 divided by 2. So there is an invisible multiplication between the 10 and the s, so we could actually divide what is 10 divided by 2. How about if I do this part here first? 10 divided by 2, we know is 5. Okay? And since the bases are the same, we'll keep the base. And numerator exponent minus denominator exponent. And 7 minus 6. So finally we have 5s to the 1st power. But we don't write 1st power. It's understood that it is 1st power. So the answer that we generally write it is just 5s. We don't have to write 1st power. Let's look at another example. Example number 4. Let's put in some more letters there. If we have 12a to the third b to the fourth divided by 3a b to the second. Now, what I usually recommend is that if you're using properties of exponent, fill in or actually write the exponent in so you could see it. So I would have rewrite it as 12a to the third b to the fourth divided by 3 a to the 1 power b to the second power, just so you can see what's going on. And we divide. Remember, these are all multiplication in between there, so we could do this portion here. Can it be simplified? And yes, 12 is divisible by 3, so we have 4. The bases are the same with the a, so it's a third power minus 1, b fourth power minus 2 from the denominator. Simplifying here, we have 4a to the second power, b to the second power. So, following the rule, bases are the same, we kept the base, and we subtract. Now the last example I'm going to show before I move on to my next rule is what happens if the coefficients can't be divided evenly. What do we do? For example, how about if I have 9 over 2? X to the fourth and x to the second. Well, we cannot simplify 9 over 2. 2 doesn't go evenly into 9. So we'll leave it as 9 over 2. Since the bases here are the same, we have x 4 minus 2. And that becomes 9 over 2 x to the second power. Very important, the x stays in the top. Okay, please don't write the x in the denominator. So we've looked at 5 examples, and you can practice more of them from the textbook. We'll take a short break and we'll move on to the third rule of exponent. Okay, we'll now look at our third rule of exponent, and this rule is exponents, what I say, raised to an outer exponent, or exponent raised to exponents. For example, if I have a to the second power, and I raise that exponent, or all of that, to, let's say, the third power. So an exponent raised to an exponent. Well, I don't want to use numbers for the rule, so how about if I use n here and m here? What do we do? Well, the rule states that a, keep the base, and we distribute the outer exponent to all of the exponents in the parentheses. So this becomes n times m. We will distribute the outer exponent, or the exponent on the outside of the parentheses, to every single exponent on the inside of the parentheses. So here is the rule. Be very careful with this rule, because for those invisible exponents, when the 1 is not written, you have to distribute the outer exponent. And I will show you that in one of the examples that we'll do. So let's look at our examples here. Example, if I have x to the third power raised to the fourth power, we'll distribute. So 4 times 3, and that becomes x, and I'll write it out, 3 times 4, which becomes x to the 12th power. So that's my first example. If I look at example number 2, how about if I have 5x to the second power, everything raised to the third power? And as I stated, be very careful because there is an invisible exponent here. So this is the same as 5 to the first power, x to the second power, everything to the third. And then I distribute. So 3 goes to the 1, you multiply, and 3 goes to the 2. So it becomes 5 to the third power, x to the sixth power. Well, keep in mind, what does 5 to the third power means? The power tells us how many times we multiply that number by itself. So we're multiplying that number by itself 3 times. So 5 times 5 times 5. 5 5s are 25. 25 times 5 is 125. X to the sixth power. Third example. How about if I have x to the fourth power divided by y to the fifth power, everything raised to the sixth power. Keep in mind, the rule says that the exponent in the outside must be distributed to everything on the inside. So there's nothing in the parentheses for us to simplify. So I now go ahead and I distribute. 6 times 4, so that becomes x to the 24th power. And I also have to distribute that 6 to the 5 divided by y to the 30th power. They are different bases, so I cannot subtract any exponents. Looking at another example, example number 4. How about if I have 12x to the fourth, y to the third, divided by 2x, y to the second, all of that raised to a second power. Now it looks very complex, but if you notice, we can look at the inside of the parentheses and apply rule number 2, which stated that if the bases are the same and we're dividing, okay, we could subtract. Keep in mind there is an invisible 1 here. Okay? So 12 divided by 2, and I'll keep it in parentheses, that becomes 6. X, we have 4 minus 1. And then y, 3 minus 2. And don't forget, all of that is raised to the second power. So we have 6x to the third power, y to the 1 power, all of that to the second. And we can now distribute. The 2, keep in mind there is an exponent here of a 1. There is an exponent here also of a 1. So we will distribute. 2 goes to this 1, so that becomes 6 squared. 2 goes to the 3, that becomes x to the 6th. And 2 to this 1 that we have there, that becomes y squared. 6 squared, as we know, is 6 times 6, so that becomes 36, x to the 6, y to the second power. So these are very common where you'll have to simplify using order of operation, we simplify the parentheses first before we start distributing the outer exponent. Okay. Okay, let's look at our fourth rule. And our fourth rule, we'll look at how do we deal with exponents that are 0. So generally the rule is, I always like to use the rules that use variables. So how about if I have a to the 0 power? Well, anything to the 0 power is equal to 1. So here is the general rule. Example. X to the 0 will be equal to 1. because the exponent is 0. 5 to the 0 will be equal to 1. Any letter of the alphabet to the 0 power is equal to 1. A to the 0 is equal to 1. 1,000 to the 0 is also equal to 1. Now, be very careful with the way it's written. Okay? Example number 2. How about if I have 5x to the 0? Now, think about it. It means 5 times x to the 0 power. So, 5 times x to the 0. Well, x to the 0 we know is 1, but that is 5 times 1. And 5 times 1 is equal to 5. So be very careful when we use the 0 power. Be very careful. On the other hand, example number 3, what happens if I had 6x, everything raised to the 0 power? Well, we have learned that in one of the past rules is that the exponent to the outside must be distributed to all of the exponent on the inside, assuming that there's no simplification to be done in that parentheses. Well, there's nothing to simplify here, so there is an invisible exponent, x, for consistency. It is 6 to the first power, x to the first power, all of that raised to the 0. And then I can distribute. So 0 times 1 becomes 6 to the 0. 0 times 1 becomes x to the 0. And we know this is 1. 1 times 1. And the final answer is 1. So be very careful with the way here, everything is raised to the 0 power. And we've said that anytime the power of everything is 0, the answer is 1. In this case, only the x was raised to the 0 power. So we have to be very careful with the way it is written for these rules. Okay. Let's look at our fifth rule. Fifth rule, we will look at the negative exponents. And in 2 of my past examples, we've seen that we have left some 2 answers with negative exponents. So I would strongly recommend after we finish rule number 5, you look at your notes and see if you can go back and fix those 2 problems that we have left the store with. So the fifth rule indicates that how do we simplify exponents when they're negative? What do we do with negative exponents? For example, a to the negative n power. Well, what it means is the negative sort of tell us that we have a fraction. So we have 1 over a to the positive n power. And that is the rule that we will follow, or the property that we must follow. So I'm going to show you an example or 2, and then I'll show you what do I usually think, or what do I tell my students when I'm looking at this rule. So the first example we will look at, how about if I have x to the minus 2 power? Well, I know it's negative, so it has to be a fraction. So it's 1 over exactly what's there without the negative in the denominator. So it's 1 over x squared. The same thing applies for a number. How about if I have 5 to the negative 2 power? So it's 1 over 5 to the second power. And we know 5 to the second power means 5 times 5, which becomes 1 over 25. Let's look at example number 2. How about if I have x to the third power, y to the minus 2 power? Well, I cannot leave my answer, or it is strongly recommended that we do not leave our answer with a negative exponent. So I can't leave my answer, or I can't leave this problem because it contains a negative exponent. Well, if I had to write this as a fraction, okay, what we could do is write this as x to the third, y to the minus 2, everything over 1. I haven't changed anything. Now, what I usually do is look at, after all my simplification, I look at the exponent of each number or letters, the exponent. Well, let's look at the exponent of the variable x. The exponent of the variable x is positive 3, so I don't have to worry about anything with that. So I could leave it as x to the third. But if I look at the exponent of the variable y, it's negative, and it's in the numerator. Well, if I bring it down to the denominator, that will make it positive. So generally, if it's negative in the numerator and you bring it to the denominator, it becomes positive. If it's negative in the denominator and you have to take it to the numerator, the sign change. Okay? Sounds confusing, but let's look at another example. How about if I have a to the second power, b to the negative fourth power, and c to the sixth power? Well, I cannot simplify anything with a, b, and c because the bases are all different. So not much to do other than making that exponent positive. So I'm going to write it as a fraction, a squared, b to the minus 4th, c to the 6th, everything over 1. And then I inspect each letter individually. A has a positive exponent, so that will stay in the top. B, it's negative in the top, so bringing it to the bottom makes it positive. C is positive in the top, so it stays where it is. And that's my simplification. Okay? What happened if it was negative in the bottom? Well, we could look at an example of that. Example 4. How about if I had x to the third, y to the negative 6 over z to the negative 2. Well, the bases are all different, so I can't do any simplification, but I could start moving things around. The x has a positive exponent of 3, so that stays where it is. The y has a negative exponent, so by bringing it to the denominator we'll make it positive because it was in the numerator. The z is negative in the denominator, so moving it to the numerator will make it positive. So I have z to the second power. And that's my final answer. Now keep in mind, I could apply a few rules in one problem. I could incorporate all of these rules into one problem. Yeah? For example, let's look at another problem. We'll take these off. How about if I have 6x to the third, y to the fourth, divided by 3x to the 7, y squared? Let's see what happens. Well, we have same bases. X is numerator, denominator. Same basis here, numerator, denominator. So we have learned in one of the prior rules that when we're dividing and the bases are the same, we subtract the exponent. Well, we have coefficients here also. So 6 divided by 3 is 2. So that becomes 2. The bases here are the same, so we keep the base, and it's the numerator minus the denominator. The bases here are the same, so it's the numerator minus the denominator. Well, 3 minus 7, that becomes negative 4. 4 minus 2, well, that's positive. That's the second power. But I cannot leave my answer. I'm sort of finished, but I can't leave my answer with a negative. Well, this is the same as if I write 2x to the minus 4 y squared over 1. And let's investigate each one of them. What's the exponent of the 2? Well, the exponent of the 2 is an invisible 1, so it's positive, so it stays in the numerator. The exponent of the x has a negative exponent. It's in the numerator, so by bringing it to the denominator, it becomes positive. And realistically, I'm following the rule, okay? If it's negative, it becomes 1 over it. The exponent of the y is positive 2, so that stays in the numerator, and I have a positive 2 here. Okay. Recommendation, once again, please try as many problems as these from your assignment and from the textbook. The last rule I will look at today for this lesson is fractional exponent. What does it really mean for an exponent to be in fraction form? I'll write the rule a n over m power. Well, we could rewrite this. Anytime we have a fractional exponent, we'll have some form of a radical. So we have, or a root sometimes, a, which is the base. The denominator is the index, so the mth root of the a to the n power. Now, be very careful here because the denominator, if you notice, always tells you the root. So if the exponent was 1/2, it means the index of the root would have been 2, so that's called a square root. If the exponent, the denominator of the exponent is a 3, then that will be a cube root. If it's a 4, it will be the 4th root, and so forth. So when you're dealing with fractional exponent, the denominator tells you the root. If it's a square root, or if it's a 3rd root, or if it's a 4th root. So here is my rule. And what we're going to do now is look at some examples. Example. What does it mean for x to the 1/2 power? Well, we know what 1/2 is. 1/2 means square roots. It's another way of writing square root. So this is the same as the square root of x to the 1st power. And I'll put it in there and then rewrite it. Well, generally when it's a square root, we don't write the 2. So it just means square root. And x to the 1, we don't have to write the 1 power because it's understood. So these two things are the same. Because this is called a square root, so that invisible 2 is actually there. When it's a square root, we don't have to write as the index is 2. And this is very common, and we'll see a lot of these later on. So be very careful. Remember that 1/2 is really square, another way of writing square root, the 1/2 power. Likewise, we could have the 1/3 power if we have a to the 1/3. What it means is the cube root of a to the 1st power. Well, as I said earlier, we don't have to write 1 because it's understood, it's a 1. But we do have to write a cube, so it's the cube root of a. That's a 3 here. Let's write that properly. It's the cube root of a. So if the numerator is 1, we don't have to write it. But what happens if the numerator is not 1? Example. What happens if we have a to the 2/3? Well, it means we know that the denominator tells us the root. So it's the cube root of a to the 2nd. And we can apply this also to numbers. Okay? Example 4. What is 9 to the 1/2 power? Well, 1/2, as we said earlier, is square root. So this is the same as the square root of 9 which we know is 3. That's our final result. So the fractional exponent is just another way of identifying when we have a root. And you should be able to know, if I give you something with a root, how do you convert it back to a fraction? For example, example number 5. What is the cube root of 8? 8 to the 1/3 power. Well, rewriting that, it's the cube root of 8 to the first power, but the cube root of 8 we know is 2. Yeah? How about if I give you something in radical form? Example number 6. If I give you something in a radical form, what is the cube root of x to the 5th power? Well, if I had to rewrite that, it's a cube root, so I know that it's going to be x and the denominator will be 3 because of the root. It always goes in the denominator. And the power is the numerator. So it's x to the 5/3 power. So you should know how to write both ways. If I give you this way, you should be able to put it in exponential form. If I give you an exponential form, you should write it in radical form. Okay? I would like you to look at the assigned problems and please apply the rules that has been explained here to your problems. I'll finish here with exponents for now and we'll continue.